update function to compute the optimal values. It can be defined, you can use these formulae to define it, so forth. If the state is defined as R of S, then you can use this formula. Whereas if you use this definition for the reward, you can use the other one. And for value iteration algorithm, you basically just calculate the values in each state for each iteration and you keep on updating. So up to until the optimal values converge, you keep on calculating them for each iteration. And then this can be used to compute the optimal policy. Yes, go ahead.
You know if the equations will be given to us in the exam?
You need to know this.
Yeah.
You remember?
Wait, what was that answer?
Memorize.
Wait, to memorize?
Okay. So the question was whether you would need to memorize the equations, and yes, would be better that.
Ideally, the MPP equation is just like a probability equation over expected states. So even if you have a good conceptual understanding, you can count with the equation at any given point of time. You really don't need to memorize it.
If you already come up with it, it probably shows that you should review it to get some intuition
Yeah.
behind the equation.
So let's move on to a value iteration example. We have the same example from before, but now we have a discount factor of 0.1. So for the first iteration, initialize with immediate rewards. We know that we only get immediate rewards in the exit states. So 10, 1, and the rest of them are 0. So then you can write the V0 values for each state, so forth. And with respect to these values, we can compute a policy here. So in this, we take the action exit, which results in this reward. So you write exit here. And similarly for this state E. And for the other states, you take either of the actions you take, you get reward 0. So either of the actions are fine. So this is your policy to begin with for now. Now we take the values we got from the previous iteration and move on to the next iteration with respect to that. So here I have given a computation for one of these possible things. The other computations are similar, so I have not mentioned them again and again. And the values are intuitive, so we can just walk through them without much of calculation. So for V1, it's going to be a terminal state, so again you end up with 10 and 1. But now for iteration 1, the value of V can be computed with respect to this. That was not there before that. So now how you would do that is, you would do the discount factor into max of left and max of either left or right actions. So this formula is basically the one that we saw in one of the previous slides, where the reward was defined with respect to SA, S dash. So you have no immediate reward, then you have this value 10, which you get from here, basically, value 10 here, multiplied by 0.8, which is the transition probability, plus for the other action, which is 0 reward, and again the value of 0 with 0.2 probability. So that gives you, and similarly you calculate for the right action, and computing these two, you will see that the left action is has a maximum value. So you will choose that as the value here, and that will be your policy also. Similarly, you will compute for D, and you will see that it will also give you a right action. And for the C state, it will you still can get 0 and 0 at both the sides, so you still get a 0 here. Any questions so far? Okay. Now, oh, okay.
So when we compute in the policy improvement, we use the values from
So policy improvement will come to later. This is just value iteration.
Okay.
So policy improvement we'll see at the end of this. So I'll move on. So for the next iteration, that is iteration 2, you carry forward the values that you had in iteration 1 and compute these again with respect to those. Similarly, what you have, so whatever computations you did before, you do them. And this time, since you have these two values for B and C, you can compute a value for C with the same formula. Let's not delve much into it, it's just math. Then you see that, intuitively also you can see that the action, if you do a left action, it will give you more reward. So the action which gives maximum value is the left action. And this is your policy at the step 2. Here for ease of computation, I am just taking the optimal values correct to decimal 2 points. So now taking these values, we move to iteration 3. When we compute the values for iteration 3, we see that with respect to decimal 2, the values do not change. So our optimal values have converged. So that means we have found our optimal policy. And if you do multiple iterations after this, you will see that these values up to decimal 2 will not change. So at iteration 3, when we see that the values are same as before, we stop. And that means that this is our optimal policy, and this is our optimal value. So discount 1 and correct to decimal 2. Yeah,
So
go ahead.
would you say that your values converge after 2 steps then?
Yeah, because I just considered correct to 2 decimals. If there were 3 decimals, maybe it would have taken longer. Yeah. Go ahead.
How did you get the value for C?
The value for C was gotten using the same formula. It was, I can compute it here. So you used these two values. So let me just do it. V2 of C is basically a discount factor in plus into max of left or right. So 0.1 into max of, you have 0.8 which is the reward into 0.8 probability plus the immediate reward which is 0 plus 0.08 into 0.2 which is the right probability plus 0 plus this was just your left action. Now for the right action we have 0.8, 0.08 which is the value into the probability which is 0.8 plus 0 and 0.8 into 0.2 plus 0. So if you can compute these values, you would see that this value has higher value than this. So that corresponds to this number into 0.1. So you would find that it is 0.06. So that's how you compute it for C. Yeah, go ahead.
Is this considered a non-stationary policy or stationary?
This, if you see later, so in the beginning it would be non-stationary in a way because you have multiple policies. It's actually still consistent, but it has multiple policies because there are like directions in both of these. But as you go ahead, you will see that the policy, you only get one consistent policy as you go through the steps.
So is there a relation between the iteration number and the K steps to go in a non-stationary policy?
So it is not going to be non-stationary. It's going to be a fixed
Your
policy.
voice is getting recorded. Please keep it down. In that case, why would you ever land up with a policy that is non-stationary? Because since you have infinite time left, and whenever you are in a certain state, taking one action will always yield the maximum value. So you wouldn't essentially think that if I'm here, I will take this action with this probability, that action with that probability, because you don't need to have a non-stationary policy when you have an infinite horizon. You can always take that, which will always maximize your reward from that state.
So if you had discount factor 0.9, you would have gotten a different policy here. Okay, so let's look at policy iteration. So policy iteration, for policy iteration, you start with the random policy, then you do two steps, policy evaluation and improvement. You do these two steps until the policy converges. So here the equation that you see here remains the same as before. The only difference here is that you have a max function over all the set of actions. Now this max function is no longer there because you're evaluating the policy with respect to a fixed policy. So you already know what actions you're going to take in that policy. So there is no maximizing over which action gives better optimal. And for policy improvement, for each state, you will now see what action maximizes from your previous policy. So, and with that, you will update your policy I to policy I plus 1 with actions that give better optimal values. Oh, sorry, better values. So let's look at some examples here. So first let's look at policy evaluation. Here the problem is same as before, only the differences are these, transition probability and discount factor. Now your transition probabilities are successful with probability 1 for all the actions. And the discount factor is 1 for easy computation. So say you were given this policy. So how do you evaluate this policy? So for that, what we do is we start like we started before. For if you take the action exit, the immediate reward that you would get is 1. If you take action right in this state, the immediate reward would be 0 for all. So from this, you just do iterations until you see that the values have normalized, the values have converged. So if you do this further, you will see that if you take action right at this state with probability 1 into the reward 1, and even the discount factor is 1. So you will see that you get value 1 here. And then for the others it will still be 0 with respect to the previous step. Yeah?
Yeah, so on the homework, I was told by several TAs that, for instance, in A, when you're in a terminal state, no matter what action you take, or I should say,
Yeah.
that should always be a terminal
Right,
state. You don't
right.
have an
But
option.
here you know that you're not taking an exit action.
But that's what I was told is in that state.
Yeah, that is when you're doing the iterations, like value iteration. If your policy is right away given, then you will have to take that action, no matter what.
It depends on the problem set up. If going into the policy state, if going into the terminal state, the one marked there, if that's actually the terminal state, then it means that there's only one action there, which is to exit. So it's possible that you can actually have some imaginary exit state, and if you get into this last state here, the only thing that you can do is transfer to that imaginary exit state. In some problems, and I realize that the way that they're set up is inconsistent, in some problems, if you get to what's marked as a terminal state, if you can leave the terminal state, it's not really a terminal state. It means that you could also have additional actions.
Okay, so that means on the last question, on value iteration, what we did should not have been
No,
correct.
there you
Because that
put
one
that.
also said that you could take exit or left or right.
Yeah, but then you took exit because you were doing the best thing possible there. And exit, and here the thing is your policy is already given to you. So you have no other option but to follow the policy. So given that policy, what would be your rewards? That is what we are comfortable with. But if it's a terminal state, in the previous thing, you would write whatever the value, say 10, no
So
matter what.
essentially for your value iteration, you would calculate the max over on an exit, and in an exit state, you would calculate the max over the right action, a left action, and an
So
exit action.
what really
And the exit
changed?
action will always be removed, like if you define that.
And in this problem, the reward is on the transition out of that final state, so you don't actually get to the
So it's, the rewards get gotten on
the transition from those edge states to that.
So what really changed here was this max, right? You don't have this max anymore. So because of that.
So, for instance, if we're in B and we had a left action, then in order to get that reward, you have to go left and then another action, exit. You wouldn't get the reward on the transition.
So if you go further with this thing, you would see that in the end you would get 1, 1, 1, 1 because this reward basically gets propagated throughout. And so your values for all these will be 1. Because you're just following that policy. Okay. So let's look at another example. Here you're taking actions exit, exit, and then right, right, and left. Sorry, left, left, and right. And same method. You start now again, and you see that this is the reward here, and for the rest it is 0. But when you take left action here, in the next step this happens, and in the next step after that, you see that this is what happens. This is a very intuitive example. You just see how the rewards are basically propagating because of the action that you're taking of the fish policy. And so your solution would be 10, 10, 10. So next, let's look at
The fourth state may also get a thing.
Going
No.
it's
The policy.
you're just following the policy. You're not really doing the maths.
But you're giving the policy.
You're just sorry.
Aren't you including the policy?
No, this is
No,
evaluation.
this is just policy evaluation. Okay. So we will go to now. We will look at policy iteration, where the step was to first evaluate your policy and then improve it. So now here, what we have is the discount factor is different. The problem is same as before. Successful with probability 1, all the actions. So when you are here, now this is your given policy. So once again you evaluate it. You will see that this is 10, this is 1, 0, 0, 0, and at the next step, what happens is you have this 0.9. So your 1, so your 10 gets multiplied by 0.9, which gives you 9 here. 0 again for the previous state, and this becomes okay. So this is 0 because you're also going in this direction, and so you're just following that. Here also you're now going in this direction. So with respect to that, it's again 0. So this is what your evaluation will look like: 10, 9, 0, 0, 1. Okay? Now in the next step, now you've evaluated your policy. Now in the next step, you will improve it. So basically you will say what action maximizes your value in each stage. So in exit, it still remains exit because that itself is the max. These two remain as is. In this one you saw, yeah, of course, going right is the way to go, but left will give you lesser. Sorry, going left, because right will give you lesser. Sorry. And for this one, you will see that if you rather go right, because you have 9 here and 0 here. So if you rather go right, sorry, if you rather go left, you have better max, like better value. And here, if you instead go right, then you will have higher value. So this is what your policy will improve in I+1 from this. So now, yeah. go ahead.
In E, are you allowed to make any other action other than the exit action?
So that was the question he asked. As long as you are following the policy which is already given to you, you will just like if the in the given policy it is exit, you will follow exit. If it is left, you will follow left, and so forth. But if you are doing value iteration where you're trying to maximize the values, you will select the exit.
But if you're doing policy improvement, why do you need to stick with the policy you're given?
So the point of policy improvement is to make your next policy better than the previous, so you're maximizing from the previous step.
So here, when it is on, we are on state E, the better values we'll get from the left action, right? Because 10 will propagate to that point.
Right. That's right.
Not from the exit.
But you're just considering this current thing. So with respect to that, the 0 is there.
And if we do it one more time,
If here
I
there
plus
was 10,
3.
Ideally,
I plus 3.
if here it was 10,
propagate
it
to
might change.
so that will change. We can change, right? That.
Yeah.
over
Okay.
iteration steps.
Yeah.
Okay.
Alright guys, I'm going to try to cover all of the reinforcement learning that you've learned so far this semester in very little time. So after this, you have a class you can go. I'm probably going to stay and continue through the slides. If you can do that, it will probably be worthwhile. So there are several forms of reinforcement learning. We're going to start with passive model-based reinforcement learning. So for reinforcement learning, or in Anna's slides, you were given the model, and you were asked to solve, to calculate the value function, or to calculate the policy. In our case, we aren't given the model, but what if we still want to be able to learn the value functions of a given world, of given states? Well, it's possible to do that, and one way is using model-based learning. So in this version, you're going to try to learn the model, or you'll learn an estimate of the model, and then you'll use all of those algorithms that Anaka just showed you to do exactly the same thing and calculate the value function. So we start out by observing an agent acting with some policy pi. So you're watching somebody who already has a policy, and what you observe are sample trajectories that look like this, where you have state, action, reward from the first state to the last. Now, to get an estimate of the model, you're going to calculate the maximum likelihood of the transition function and the reward function. Now, you might be wondering, what is the maximum likelihood? You might not have even used that term when you learned it. What maximum likelihood is, in this case, for the transition function, it's the likelihood of, the maximum likelihood of the probability of being in state S, taking action A, and transitioning to S prime, which can be calculated by the number of times that you were in state S, took action A, and landed in state prime, over the total number of times that you were in state S and took action A. That will give you a probability for SA S prime. And then we generally assume that the reward function is very easy to learn, because we literally see, we see that we get the rewards directly from our sample trajectories. So we generally assume that this is pretty easy to get. And we then evaluate the policy pi by calculating the value function using value iteration, policy iteration, or whatever you would like. It's also possible at this point, once you've evaluated the policy and gotten some v pi of s, that you could also then improve, you could create a new policy and improve it over the policy that was being followed by whoever was acting in the world and giving you these trajectories. But in this case, we get the value function, but that doesn't actually allow us to actively act in the world and to improve our policy. So another thing that we do is active model-based learning, which is going to start the same way. We're going to, except in the last problem, we were observing somebody who was following some policy. in this case, we're going to start acting in a world following some random policy. And we'll again do maximum likelihood to get an estimate of the transition function and the reward function. And we'll again calculate V star for the estimated model. But now we're going to use the values that we get there to generate a greedy policy pi, a new policy. Better than the one that we started with, which was just acting randomly. Now, we're going to get new traces. We're going to start using our new policy in this world, except we're going to act on it epsilon greedily, which means that 1 minus epsilon percent of the time, we're going to exploit what we already know by using what our policy pi tells us. But for an epsilon amount of time, we're going to again just act randomly. And this is going to give us the exploration and exploitation that we need. That should be exploration. So and now we'll update the model, also including the new traces that we've gotten using our better policy. And when we have those new traces, the new estimates, we can then calculate a new V star, and we can repeat this process until our model becomes as accurate as we would like. Now, I kind of waved my hand at the exploration and exploitation here. So you might be wondering, why would we want to start acting randomly when we already have a policy that is a greedy policy? It should be good. And I'll get to that with a question. So imagine that I'm giving you a job. And instead of giving you a paycheck at the end of every week, I tell you that at the end of each week, you're going to come into my office and I'm going to have you open 1 or 2 doors. Whatever value is behind the door that you open is going to be the amount of money that you get for that week's work of work. So let's say after your first week, you go in, you open door A. You get a value of 2. You get $2 for working that week. Great. And you're like, well, that kind of sucks. So the next week, you go in and you're like, well, this time I'm opening door B. I know nothing about it. Well, door B gives you a value of 1. If you were to act greedily, based on the values that you know here, you're going to open door A every time because it gave you double the amount that door B did. And so you would do this, you have some values, you act greedily, and now door A is the door you're going to open every week. You're making $2 a week. But what if instead of just acting greedily, we also continue to explore for some percentage of the time? So again, you go in, you open door A, now you get a value of 3. Okay, so it's not the same value every time. The 4th week you go in, you open door B, you get $1 million for that week. So clearly, there's some value in continuing to explore the state space. Now let's say maybe door A only gives you values 2 or 3 with equal probability. Maybe door B gives you values between 1 and 1 million with equal probability for each value. That's something that you would eventually learn, and as you learned it, you would start decreasing the amount that you open door A, and increasing the amount that you actually do, which is going to start leading towards door B. That's going to converge to an optimal policy. So, that was model-based learning, where you didn't have a model, but you learned it. It's also possible to learn without coming up with a model at all. And we start out with the naive case of the Monte Carlo method. Also, you guys called it the direct policy evaluation. So, in this case, again, you're given a policy. This is going to be passive learning, where you're just watching somebody act in the world. You have some policy, and this policy shows if you're in state B, you go right, state C, you go up, state E, you go up. And if you're in states A or D, the only action that you have, which is related to your question, is to transition from A to X or D to X. So this is, of course, going to be in your policy because it's the only action that's possible. So with Monte Carlo learning, you'll again learn from a series of episodes. So we have one where we go from E to C to X, or E to C to A, B to C to A. And you'll observe these episodes using the policy. And then you're going to calculate V of S using the average return from state S to the end of the episode for every time that you saw state S. So if you're in one place and in one episode, you see state S, and from S to the end, you got a reward of 10. And in the next episode, you also saw state S, and between S and the end, you got a return of 20. Then V of S, for those two observations, is going to end up being 15. It'll be the sum of the returns from S to the end of the episodes over the total number of times that you saw state S. So, to calculate V of A, using our 4 samples, our 4 trajectories through space, we see A 3 times, here, here, and here. So we add up the total return from state A, which is 10 for each, and divide it by the total number of times that we saw it. There's 10. Same thing for B. We see B twice, and from B we see -1, and 10, so that'll be 8. And we also see -1, and -10, so that'll be -12. We sum them up, we divide it by the total number of times that we saw B, and we get our value estimate for B. We'll do the same thing for each other one. And I guess let's take a look at C here. Notice we see C 4 times, but C starts in the middle of the transitions, which means that the first return for the value of C in this sample is going to be -1 plus 10. Not -1 plus -1 plus 10, -1 plus 10, because we started at C. So you do the same thing for each of the episodes, and you get the values for each of them. That is the Monte Carlo method. Now there are some problems with it. Notice that states B and states E only ever went through C. So, and this is supposed to represent the values that you get for being in this state and going forward. So why is it that even though B and E both go through C, B, C, and E all have completely different values? Surely they should be similar. And that's because the Monte Carlo method doesn't exploit the Markov properties. All it does is it looks at the total return at the end of it and updates it. So because we started with B and ended up getting -10 somewhere, we got a bad value. We started at E, we got a lot of points back, we got a high value. So this means we're actually wasting a ton of information. B has no idea that he has any probability that he could get a high value for A. Also, notice that in order to do this, we have to take all of our episodes at the beginning. And after we have those episodes, we can compute the values. But if we were to get more episodes later on, we would have to recalculate our values of S for all the old episodes plus the new episodes. However, that problem can be fixed by using an iterative method. Now here, there's a lot of notation, so I'm not going to walk you through it. But the important part is this. This first line here is what we just did for the Monte Carlo simulation. This second line here is the